So this problem is something in disguise. So I'm going to try to come up with a similar problem. Remember, you can always change the variable of integration here. See how, because everything here is a c, you could change that to match a different variable. You could change it to match a t. You could change c into an omega. They're just variables. Let me put down the Fourier transform pairs here. So we had big X of j omega is equal to minus infinity to infinity of x of t e to the minus j omega t dt. And then we also had little x of t goes back to, by the Fourier transform formula, going from minus infinity to infinity of big X of j omega e to the plus j omega t d omega. So those are a couple of things that we have. There's actually, in this case, there's a couple ways to do the problem because there's a couple things that match here. How about this? Let me do another example. I'm sorry I'm really hesitant here because it's so hard to explain how to work that problem without instantly giving away the answer. Like, it's nearly impossible. So we do have this transform pair that's e to the minus, would say something like e to the minus at ut transforms, wrong class, Landerman, transforms into 1 over j omega plus a. That's one of the Fourier transforms pairs that we have. Suppose you needed to solve this integral. Integrating from minus infinity to infinity, 1 over j omega plus 5 e to the minus j, how about 8 omega d omega. So if I look at this here, this more or less looks like an inverse Fourier transform. What would I need to do to make it match up? I could have 2 pi divided by 2 pi, and that would make all the stuff in here. That would actually make it look like this inverse Fourier transform pair. Notice I would wind up with the 2 pi sitting out in front because I would need something to make that 2 pi. And what does this guy equal then? Well, this is something like 2 pi, right? Because I have 2 pi sitting out in front here. This looks like an inverse Fourier transform. And if I had t here instead of 8, you would immediately recognize that as a Fourier transform. So you could say, well, this is just inversing this transform. So I could write e to the minus, what's a here? A would be 5. So I'd write 5 t ut, except I don't have a t there. I actually just plugged in a number. So I could evaluate this whole thing at that t minus 8. This would be 2 pi e to the 8 times 5. I guess that's 40. Incidentally, in this problem, actually, you could work it both ways. I think one way is slightly easier than the other. Just the 7 is a thing that you're plugging in, either for an omega or for t. I've just already plugged it in for you. And the only thing that makes this tricky is the fact that I disguised a variable here as c. And so if you look at the pairs up at the top, you could actually use either of these. You could try it both ways, and you'll see that they would both give you the same answer. Let me do another example of this particular kind of problem. The pair I'm going to show you is from the next lecture, but which I'm going to make after talking to you now. Okay, so this is a boxcar function. So this Fourier transforms into a thing called a sinc function. So here I've got omega L over 2 all over omega divided by 2. So suppose somebody came up to you on the street and said, well, do you know how to do this integral? Sine smiley face L over 2 smiley face over 2 e to the plus j 8 smiley face. No, that's not sneaky. I need to be more sneaky. Now, if you just were handed this on a calculus exam, this looks kind of like a Fourier transform because it has a minus here. But if I look at it, well, if I looked at my table, if you look at the table, I only have something like this. So I have to do this using an inverse transform. Another hint I might have given the student is to put something like 12 pi, the 1 over 2 pi here, to make it look more obviously like a inverse Fourier transform. So what would this guy be? Well, this guy would be like let me go ahead and write it out as u's here. U of t plus L over 2 minus U of t minus L over 2. It looks like we're taking here an inverse Fourier transform, and that would be obvious if I changed all of these smiley faces into omegas. So if this is an omega and this is omega, it's now obvious we're taking a transform. But what's playing the role of t here that we would plug in? It would be this guy. Because in the original transform, there's a plus, but here I have a minus. So it's basically this transform evaluated at t equal minus 8. Oh, you know what? I didn't really finish specifying the problem. I would have to make something for L. Let's put in 5. Let's make 5 be L. L is 5 here. My boxcar actually goes from minus 5 over 2 to 5 over 2. I evaluate it at t equal minus 8, and that would be outside. So this whole integral here winds up equaling 0, right? Because it's outside. And think about how tricky this would be to figure out without this Fourier transform theory. If you just had this integral with the sine stuff over the stuff, and you've got this exponent here, to somehow figure out that was 0 using your standard freshman calculus techniques would be astonishingly hard. So let's do a slight variation of this. What if this wasn't here at all? A slight variation of this. And let's let L be 100. Okay, so if L is 100, my boxcar is here going from minus 50 to 50. Then if I plugged in t equal minus 8 there, obviously that would be within that realm. So then I would get 1 out. But again, imagine how difficult it would be to figure out that integral from scratch. So that was an extraordinarily long-winded attempt to explain what's going on in this problem. Let me just mention one more thing I might do to disguise this. What if I had put, instead of 1 over 2 pi in front, what if I had put 10? Well, then you would still have to do the same trick. You would probably have to say, if I put 10 in front here, let me erase the 1 over 2 pi. Erasing. Okay, so if I put 10 here, then I would still need to do this trick to get this 1 over 2 pi. And that 1 over 2 pi, it shows up like in quantum field theory, which is this weird psychotic theory of physics that appears to be true, but also is just weird. I might do something like this so I could wrap all of this together to be the Fourier transform, but then I would have to multiply these guys, and my answer here would be something like 20 pi. That's another way I could disguise the problem, because if I don't have a thing here that looks like 1 over 2 pi, then it's not obvious that it's a inverse Fourier transform. And if I really wanted to be evil on an exam, I could set up something where you really need to use the forward transform, but I have a 1 over 2 pi somewhere in there. You'd have to do something to get rid of it. There's all sorts of ways that I can to make it more difficult to see. You can see that immediately the way I pick the C here, right? If I pick that to be T or omega, then suddenly the problem's a lot less disguised.